Hello everyone, my name is Sana Mulla and I'm here to present my ISE activity, which is presentation on principal stresses in rocket nozzles walls during combustion. First up, we need to understand what a rocket nozzle is. So a rocket nozzle is a very important component of the propulsion system. It transforms the high pressure, high temperature gases from the combustion chamber into high velocity exhaust, which indeed produces thrust. So during combustion, the nozzle goes under a lot of stresses and strains. It undergoes high internal pressure, extreme thermal gradients, which can vary up to 3000 Kelvin at the inner surface, and also dynamic loads, which are during ignition and shutdown. So these loads they create complex stress state, and analysis of these principal stresses is very important to predict the material behavior and to ensure safety and to also avoid the failures. Here is a simple nozzle structure overview. So rocket nozzle generally has main three regions: divergent, convergent, and throat. So a convergent region, it accelerates gases to the throat. The throat has a very minimum area, but it has the highest pressure and temperature. The third and the last section is divergent section, which expands the gases to a supersonic speed. It also has walls. These walls are typically thin and axisymmetric, and they are subjected to very high internal pressure and heat flux. The material generally used to manufacture the rocket nozzle is nickel-based superalloys like inconel and hastelloy. Also, refractory metals are used like niobium and molybdenum. There are also carbon-carbon composite which are used and ceramic matrix composites. Moving ahead, we have the type of stresses acting on the nozzle walls. So there are five types of stresses which act on the wall of the nozzle. First up, we have hoop, which is also a circumferential stress. It is due to the internal gas pressure. It is tensile in nature and it acts along the circumference of the nozzle. The second one is longitudinal or the axial stress. It causes due to pressure which is acting on the nozzle end surfaces. It is tensile in nature and it acts along the nozzle axis. At the Similarly, we have radial stress, thermal stress, shear stress, which act on nozzle, in different directions like radially inward, through walls, and tangential or longitudinal. Moving ahead, we have the thermal stresses. So when the inner surface is much hotter than the outer surface, so there is expansion of hot inner layers which is restricted by the cooler outer layers, which causes the thermal stress. The thermal stress is given by sigma Th E alpha At. Here E is the Young's modulus, alpha is coefficient of thermal expansion, and delta T is temperature difference, which is along the wall, which is the outer and the inner layer. So the distribution of this thermal stress, it depends on the thickness of the wall, the thermal conductivity of the entire material of the nozzle, and the cooling method, which can be regenerative or radioactive. So the thermal stresses, they can be compressive on the outer surface and tensile on the inner surface. So this was thermal stresses. Next up, we have distribution along the nozzle. So as we have seen before, there are three main sections, which is convergent, divergent, and throat. So we are going to see the stress distribution along these sections. So at the throat, it has the highest internal pressure, which is maximum hoop and longitudinal stress, and it also has highest thermal gradient. It is a very critical region for designing and cooling. Next, in the divergent section, there is pressure there. The pressure here drops very sharply, and the thermal loads which we have, they remain high. So due to high temperature, the stresses here are reduced. In the last section, which is convergent section, it has the The stress here is dominated by chamber pressure and attachment loads. It has stress counter diagrams, etc., which vary along the nozzle length. Next up, we have the effect of temperature and material properties. So, as we've seen, the nozzle undergoes a lot of high temperature pressure. At high temperature, material, it will strengthen, the modulus decreases here. So creep and thermal fatigue becomes dominant failure modes. Composite and refractory material resist these effects better than the metal. So composite and refractory materials are very, much preferred for the construction of the nozzle. Accurate modeling is required depending on the temperature dependent material data as we can see in the figure. Moving ahead, so as far we have seen the principal stresses in rocket nozzle walls, they are caused due to internal pressure and thermal gradient and also mechanical loads. We've seen hoop stress, then thermal stresses. Uh, to conclude, advanced materials like super alloys and composites are much preferred for the manufacturing of the nozzle, and efficient cooling methods are also essential. And there has to be done some accurate thermomechanical analysis as well. So a well-designed nozzle, it ensures safe operation, long life, and optimal thrust efficiency. Thank you.